Final application of Fourier methods, I want to think about spatial Fourier transforms. So I've already taken some spatial Fourier transforms, that is a transform between a coordinate in space x and a spatial frequency kx, and we've done this for treating dispersion in waves. But now I want to think about taking a Fourier transform where we have two spatial dimensions. So for example, if you have an image of a cat, we have an x-coordinate and a y-coordinate. How can we define a Fourier transform that takes transforms over both of these coordinates, so we break the image up into spatial frequencies in kx and ky? And this is going to involve a two-dimensional integral, and it's going to be a little complicated. I will show you these integrals, but I really want to try and understand the way these things work from a very qualitative perspective. So I'm not going to ask you any questions where we've got to calculate in detail horrendous two-dimensional integrals of images, but I do want to try and communicate in this part of the course a way of understanding what the Fourier transform of an image might look like by looking at some of its features. And so the kinds of questions that we'll be posing are, if you modulate an image, what does that do to the Fourier transform? How can we fix that modulation? These things will become clear later. And then also relate the two-dimensional Fourier transform to diffraction, which you see in optics. And this is a really interesting and amazing application of two-dimensional Fourier transforms. So to kick things off, let's consider an image that looks like this. We're defining this image as a function f of x and y, and the function is 1 plus sine x. So this has a minimum value of 0 and a maximum value of 2. And so we can imagine constructing this image, for example, by colouring all of the maximum parts black and the minimum parts white. So the white parts here will be 0 and the blackest parts are 2, and in between we have shades of grey. So here's our image in the x and y directions. We're going to take the Fourier transform of this image in two parts. First, we'll take the Fourier transform in the x direction. What that means is that each row of this image, we're going to take a Fourier transform. So we do that. It's Fourier transforming along the rows, and what we find is the real part of the Fourier transform just has a single spike at the center here at kx equal to 0. And that's coming from this 1, because the Fourier transform of 1 is a delta spike at k equal to 0. The imaginary part comes from the sine component of this function. The sine wave transforms to delta spikes at plus and minus the spatial frequency of the sine wave. So we have a negative delta spike here in the negative part of the kx axis and a positive spike here. And together this is the Fourier transform of this sine component of this function. And so this is a rather funny construction here, because we've got this coordinate here in the vertical direction is y, but the coordinate in the x direction is kx, or in the horizontal direction is kx. So each row of this image is defined by the Fourier transform in the x direction. And because each row is the same, we have no variation along the vertical direction of these images. The Fourier transform is defined like this. So we're taking the function f of x, y, and then taking the Fourier transform in the x direction with this kernel, which has got kx in it, and integrating over dx. And as I've said, the 1 shows up in the real part, the sine wave shows up in the imaginary part, and we have positive and negative delta spikes for the sine wave. The next thing to do is to go onwards and take the Fourier transform in the y direction. We take the Fourier transform of this function here, which has the real part and the imaginary part, so I've had to plot it in two parts. This combined is some array of complex numbers in the horizontal and vertical directions. So we can take the Fourier transform of that column by column. So let's do that. And what we get is something incredibly boring. Now, it's basically 0 everywhere, except if you can see there's a tiny little spot there and two tiny little spots here and here. Let's just go back here and anticipate why this result is what it is. Well, if we take Fourier transforms along all of these columns here, which are all 0, then we get 0. The only column here which gives a non-zero result is this central one, which this central column here just has some constant value. Fourier transform of a constant is going to give us a delta spike in the center here. Similarly, in the imaginary part, all of the Fourier transforms of these columns are 0 except for this column here and this column here. So that's where this result comes from. It looks pretty boring. So the definition of the 2D Fourier transform is just an extension of that previous definition that I gave you, except now we're integrating twice over x and y with this two kernels, one for kx and one for ky. Now the 1 shows up in the real part, and I'm going to zoom up in and take a slice along the kx direction to show you what it is. And you see you have this big spike in the middle here, which is basically a delta spike. Well, of course, all these Fourier transforms here are done numerically, so a delta spike is not really a delta spike, it's just some large value. You can also see you have a little bit of noise turning up here at the values of the modulation frequency. Now the sine wave turns up in the imaginary part. Again, taking a cross section, we can see we have a negative spike and a positive spike in the imaginary component. So this is the two-dimensional Fourier transform of this very simple pattern here. Now I've motivated this two-dimensional Fourier transform in an analogous way to the original 1D transform we considered. We have some real valued function in the xy plane, and we take the Fourier transform into the kx, ky plane. We have functions that can be complex. So we see, for example, we have this imaginary component to the Fourier transform in this case coming about because we have a sine x function that gives us imaginary components. Now, in a couple of videos' time, we'll consider wave propagation. Now, waves have a phase. If we imagine a wave propagating along the z-axis, then the xy plane may have some phase, and we'll represent that using complex functions. So then we'll consider Fourier transforms of two-dimensional complex functions in the xy plane and transform them into a kx, ky plane.